For this problem, we're ultimately trying to get to an expression that describes a sinotudinal wave, the transverse wave going along here, and the general form of the equation has been written in two different ways that you've seen in your book. One is amplitude multiplied by sine of 2 pi divided by the wavelength, multiplied by quantity x position minus velocity times time coordinate. And this could be written equivalently as a sine of kx minus omega t, where k is the wave number, defined as 2 pi divided by wavelength, and omega, the angular frequency, is defined by 2 pi divided by the period. Now, some of the information that we are given in this setup is that we are told that the period, or the oscillation, is a mere 25.0 milliseconds. Pretty small. We are also told what the transverse speed of the wave element is, that is how quickly the wave will move along in the x direction. So in a sense, we're given the x velocity component of the string. I specify that because in the up and down motion, that velocity could be much, much different. So that, we're told, though, is supposed to be 30.0 meters per second. We're also told this is moving in the negative x direction, so we should be putting a minus sign there. One other important piece of information is the position and velocity of some element of the string at a certain position and time. So we are told basically that the y component at x position 0, time coordinate 0, is equal to 2.00 centimeters, and the speed, or I should say really the velocity at that instant of that little element, again at the same position and time, is 2 meters per second. Notice 2 meters per second, so pretty good amount. And also we are told this is in the downward direction, so that should again be a negative velocity for our system. So we're saying up is positive, to the right, or the positive x direction, positive, specifying that good coordinate stuff. So what we are trying to express is ultimately all about transverse waves and the mathematical description for that. Now, the first thing we want to do, though, is figure out what is the amplitude of this setup. I should also say that there's one more thing we should be including with our expression up here. In both of these cases, there should be an addition of the phase constant where we use the letter phi. And that's true in both cases here. It's supposed to be added in, and that's basically supposed to move the function left or right. We can't assume what it is, and since that's also one of the things we need to uncover, that's what we're going to have to go about and do. It also means that at position 0, time 0, the initial position may not be the actual amplitude of our wave. So, for example, if our drawing were to look like this, and if we were looking at time equals 0, this is the x dimension, this is the y dimension of our wave, saying that it is at a position of 2 centimeters, let's say right here, and going downward, we'd expect something to have a downward slope, and so maybe the sine wave like so. which means that before time equals 0, it could actually have some higher amplitude. In fact, we would expect it to, because if it has a negative velocity, it was at some previous position before. Since at some instant it had to have 0 velocity, and that must have been earlier in the past. So, what can we do to figure this out? Well, again, we can say how the y position at 0, 0 is going to equal a times sine of, and if we plug in zeros for our expressions here, we're just going to get sine then of our phase constant, whatever that happens to be. And if we were to look at the velocity at that point, and remember that velocity is equal to a time derivative of position, from our expression we should have a negative sign popping out with I should say we should have actually negative omega popping out. So I'm going to use this expression for our purposes for right now. So if we do that, we find that we're going to get negative omega a cosine divided by phase constant. And of course, in both cases, we know what values these are. In the first case, it was 2 centimeters, or I should go with 0.02 meters to keep everything in the same units. And here the velocity then was negative 2 meters per second. Now, if I were to divide the top expression here by the bottom expression, one of the things that's going to drop out is the amplitude, which is unknown to us. Omega, we don't know explicitly, but since we're given the period, we can find what angular velocity is, or angular frequency is, from that expression. And as for the phase constant, well, that's the one thing we won't know, but then it's the thing we can solve for. So first we'll give ourselves a bit of room to play around with. So we're going to divide the initial y position divided by the initial velocity, and that is supposed to then equal what? Well, note that sine divided by cosine of the same thing, that actually gives you the tangent, since sine divided by cosine is by definition the tangent function. So we're actually going to get tangent of our phase constant divided by negative angular frequency equal to 0.02 divided by negative 2. And so if we solve for this, we need to be careful. One thing we need to do before, of course, is find what the angular frequency is, which again is going to be 2 pi divided by the period, and that will give us 251 hertz, approximately. Now we can plug that into our expression that we found here, but if we're going to take the tangent function and have to do the arctan to get phi, our phase constant, we should remind ourselves that multiple phase constants can work here. So let's not just get one solution, we'll have to get multiple. Nonetheless, the expression we're going to have for our phase constant is, the solution we can get from this is 1.19 radians. So with this as our phase constant, and we'll find that any other solutions are just going to be repetitions of this, fortunately. But we'll see that if we plug that in for our y0 position, our amplitude, which is going to be a sine our phase constant, that's supposed to equal 0.02 meters. And since we know what to plug in for phi, we can find then that the amplitude is 0.0 0.215 meters, or if you would prefer, and I think I do, 2.15 centimeters. So amplitude a little bit larger than what that was the initial little bit of the vibrating object at that one position at that one instant. So we've already done parts A and B, though in a bit reverse than what the book wanted, but we can do what we want. So the next thing, though, if we want to fill out completely either of these equations, we have amplitude, we have the phase constant, we know what the velocity is because we're given that, but we need to figure out a few more things. Also, we are asked to find what is the maximum transverse speed. And that transverse speed is going to be defined by this expression if we take a time derivative with that, and the maximum amount is then when that function is at its largest. So we've already kind of drawn that before, that is supposed to be negative omega times the amplitude cosine of all the stuff that's in there. And if we want a maximum value, then that means when cosine or whatever is in there equals 1. So that's what we're looking then for max. So let's do that next. We'll start with a clean slate. So the velocity that we're looking for is supposed to then be negative omega amplitude cosine of blah inside. And since we're looking for the max value, it's going to be then negative omega times our amplitude. Well, fortunately, since we already figured out what the amplitude is, and we know what omega is, which is the angular frequency of our oscillator, we can plug that all in. And really, we should just take the absolute value of this because we're just looking for a max value and not positive or negative. We're just trying to get a magnitude here. So if we plug that in, we're going to find that the maximum velocity of any little segment of this is going to be 5.4 meters per second. And when I did that, I plugged in an angular frequency in units of hertz, and I plugged in the amplitude in units of meters rather than centimeters. You will notice that this speed here is not the same as the transverse speed itself. Remember that that transverse speed that we were given, which I decided to call Vx, that was a 30 meters per second, a whole lot faster. Now, given the expression we have, because our amplitude was so small, what that is indicating to us is that since the amplitude is how much the wave goes up and down, since the wave barely had to go up and down at all, only a little bit more than 2 centimeters, and this wave moving along at a pretty good speed, any little bit doesn't actually have to move up and down that fast to complete the full oscillation by the time the wave has completely moved through some part of the string or whatever is our object that's oscillating. So this might seem a little bit small, but this is basically, in a sense, what we're looking at is the y component of our velocity here. And so, of course, it makes sense that if we have a larger amplitude, then we have to cross a bigger distance to reach equilibrium again, and this is going to tell us basically how much time we have. Since the faster this wave goes, then the faster we need to complete the oscillation because the wave had already gone through. And since omega here, the angular frequency, is related to that velocity, it makes sense that the faster this is, the larger this value will be, and the faster we need to move through. But again, because that amplitude is so small that you barely have to, move compared to all the other speeds that we have. So, not absurd, but it might be somewhat unexpected. Now, our last step is we want to complete the expression that we have for the wave equation that we have. Now that means there's one last piece of information we need, and it could come in either a form of the wavelength or of the wave number, which are related by a factor of 2 pi. Now, how are we going to get that? So far, nothing we've done gives us that information. But let's remember one other detail, that the transverse velocity, which with my expression is the x component velocity, is related to the wavelength times the frequency. Now, frequency we're not given, but of course that has a nice inverse relationship with period. So I could rewrite this expression. And we were given the period, as I mentioned before, of 25 milliseconds. So we actually then have enough information to get the wavelength. Not too bad. So in that case then, we find that our wavelength is just going to be the velocity times the period. And of course this expression should look somewhat similar to you. This is a distance over time to get a velocity, so you can definitely tell the units work out there. And if you plug all that in, you find the wavelength for this setup is going to be 0.75 meters, or 75 centimeters if you prefer. And if instead you wanted to put that in terms of the wave number, k, which is equal to 2 pi divided by that wavelength, then you would get 9.13 inverse meters. Not the nicest unit, but that's what we have for this. There isn't a term like hertz, which is representing inverse seconds. Not my fault, I didn't come up with it. So let's give ourselves some space to do our final equation form. Since now we know the amplitude, we know the angular frequency, we know the wave number k, we have the phase constant phi, we can put this all in now. One last minor detail to remember also, that velocity up here, the transverse velocity, is actually supposed to be negative as we were given. So if we do that, our expression for the wave itself as a function of position in the x direction and time is the following. This is the following expression, and all in units of meters, seconds, or inverse meters, inverse seconds. So this was our amplitude in meters. This is our wave number in inverse meters. This is our angular frequency in hertz, or inverse seconds. So that's our final expression. Might be a little bit hard to check, but we could, for example, plug in one last little thing, of course. Let us not forget that phase constant. As you can see, it is somewhat easy to forget, plus 1.91. And that has units of radian, so it just basically effectively has no units when we plug it in there. Alright, so that's our full expression. Sorry about forgetting the phase constant. But like I say, a little bit hard maybe to check this, but of course we can always plug back in the numbers that we knew before. So if we plugged in 0 and 0 here, we're going to get the same expression popping out. Not too interesting per se, but at least we can make sure that we're consistent with what we've done before. We didn't make any calculation mistakes that way if we plug all that in. And of course we can get the velocity to pop out. We could also find what is the acceleration of any little segment of that rope as we go along, if we so preferred, just by taking 2 time derivatives of this expression. And again, specifically the time derivative, since that's how velocity and acceleration are defined, the time derivatives relative to position. In this case, since this is y, this is position in the up and down direction.